Welcome to Group 8's model portfolio for the design of an ultra-long-range aircraft capable of travelling from London to Sydney non-stop. The following video showcases the current aircraft model, how it's been developed, and how its structure allows a future team to continue the modelling work with minimal input from the original designers. The portfolio covers the overall aircraft model, including its architecture, master skeleton, structural arrangement, internal layout, system pathways, movable mechanisms, and finally, the strategy for handover. The model architecture begins with a work breakdown structure, which was used to divide the aircraft into its main modelling areas. This gives a clear top-level view of how the CAD has been organised and reflects the top-down approach used throughout the build, where the model was defined at its highest level before moving into detailed subassemblies. That same logic is then carried into the CATIA tree, where the skeleton, parameter definition, and major subassemblies are arranged in a clear and logical order. A key part of this is the parameter tree, which supports a parameterized approach by keeping the main controlling values together, rather than spreading them throughout the model. By keeping the main references and parameters above the geometry they drive, the model is easy to follow, easier to edit, and much more practical to hand over to a future team. Having shown the overall model architecture, the next step is the master skeleton, which forms the basis of the aircraft geometry. The model was built as a half aircraft to keep the process more manageable, while still defining the full configuration clearly and consistently. A key part of this approach was parameterization. Rather than hard-coding the geometry, the main spline points and reference locations were defined using proportional relationships. For example, as seen in the parameters tree, fuselage section points were created as proportions of the fuselage length, so if the overall length changed, the surrounding geometry would update with it. That same logic was carried through into the tail, wing, engine, and landing gear references, which made the skeleton much more adaptable as the design developed. For the wing and fuselage blend set in particular, the main planform and reference stations were recreated in CATIA from the earlier OpenVSP aerodynamic definition, rather than being imported directly, so the geometry remained fully parameterized and editable within the skeleton. When building all wireframe geometry, planes were used extensively throughout the stage, including offset planes, angle planes, and local reference planes to define fuselage sections, wing and tail placement, and major interface regions. From these, points, splines, and guide curves were generated as the main wireframe definition of the aircraft, as shown in the tree and on the model. These wireframe references were eventually developed into geometry using CATIA surface tools. Multi-section surfaces were used to generate the main aerodynamic bodies, while fills were used to close local regions, and joins were used to combine these into larger continuous surfaces for the wing, tail, and fuselage. The skeleton was also used to define the cutout and interface geometry. This included passenger windows, pilot windows, emergency exits, control surface boundaries, and cabin floor references. These were positioned and shaped using the reference planes, projected curves, offsets, and split operations that came from the main skeleton logic. Offset tools were also used to generate internal fuselage skins from the outer surface, which later helped define the available space for structure and internal packaging. As the design developed, some of these references were refined in response to downstream requirements. One example was a landing gear integration, where the initial geometry was later adjusted to provide the required space and interface definition. That shows the benefit of using a top-down approach, as changes could be pushed back into the skeleton and then carried through into the independent geometry. The structural arrangement was developed as an indicative internal framework for the main aircraft bodies, with enough detail to show how the major components could be supported internally. Starting with the fuselage, this was divided into two main elements, frames and stringers. For the frames, a single pad was created and then patterned along the fuselage before being split against the outer fuselage surface and the inner offset surface, leaving only the structure between the two skins. These were then further trimmed using the main fuselage openings, including passenger windows, pilot windows, and emergency exits. The stringers followed a similar process. A single pad was created from a side reference plane, circularly patterned around the fuselage, and then split against the inner and outer surfaces before being cut back using the fuselage opening geometry. For the wing, the structure was built around the main spars and a rib network. The ribs were created as repeated sections along the span, and then split back against the wing surfaces and surrounding boundaries to fit within the outer mold line. The spars were positioned to follow the wing profile internally, running behind the slat region and ahead of the main control surface cutout, giving the wing a representative internal arrangement tied to the external geometry. The wing box was then treated separately as a more reinforced and locally customized region. This was used to represent the highest strength central structure associated with the main landing gear integration and the center fuel tank area, rather than simply repeating the outer wing rib pattern directly. A similar structural approach was then applied to the horizontal and vertical tail, where the internal members were generated from the tail geometry and trimmed back to fit within the outer surfaces. Finally, the engine was based on an important reference model, since the engine itself was selected rather than designed within the project. That geometry was then modified and integrated into the aircraft assembly so that it matched the required installation. Moving on to the internal arrangement, this section shows how the main internal spaces were allocated and represented within the CAD model. The clearest way to show this is through the aircraft cross-section. Under the cabin floor, the fuselage was divided into a series of main functional zones, running from nose to tail. This includes the avionics compartment, nose landing gear bay, battery compartment, forward cargo hold, and forward auxiliary tank. Around the center region, this then transitions into the center wing tank and main landing gear bay, followed by the ram air turbine, systems bay, aft cargo region, water and waste storage, and finally, the APU at the rear. The aim here was not to model every single subsystem in full detail, but to allocate the main volumes clearly so that the aircraft packaging and interfaces could be understood. The fuel volumes were also integrated into this layout, with the wing divided into the center, inboard, mid, and outboard regions, together with a surge tank near the tip, while the trim tank was located in the tail. Above the floor, the cabin was arranged as a 150-seat all-business class layout. From a modeling point of view, the seating was built from a repeated unit and then symmetried across the half model, so that the full arrangement is generated consistently once the aircraft is mirrored. Because this aircraft is intended for an ultra-long-range mission of around 21 hours, the internal arrangement is not just about packaging, but also how the space would actually be experienced by the passenger. For that reason, the next part moves directly into an immersive view of the cabin and internal layout through virtual reality. The business class seats, overhead bins, central ceiling services can be seen, along with cabin monuments and display screens used for passenger information and announcements. Moving into the mid-cabin, the same seating layout continues, with floor-level emergency lighting shown in the green to guide passengers towards exits during low visibility conditions. The galley and lavatory area is positioned centrally between the cabin sections, helping separate the zones while still keeping passenger services accessible. The aft cabin then continues the same business class layout before transitioning into the rear service area. Here, the bar and galley space can be seen, including the main service counter, upper display screen, and emergency exits positioned either side. At the rear of the cabin, the crew rest area is provided for long-duration operation. With a 21-hour mission, crew accommodation is essential, and this area includes bunks on both sides, overhead storage, and additional cabinets, giving the operating crew a dedicated rest space within the aircraft. The crew rest area is designed to accommodate 16 crew. As the walkthrough continues, the view moves further down into the cabin, giving a clearer look at the business class suite layout from above, and showing how each unit is arranged within the wider cabin space. Perspective then moves into one of the window side suites. From the seated position, the first thing to notice is a direct outside view, with a large window opening, providing good visibility and even a clear view over the wing. This also helps show the level of privacy built into each suite, together with the overall sense of comfort and personal space available to the passenger. The view then moves into one of the center business class suites, showing how the middle seating is arranged within the four abreast central section. A privacy divider can be seen between adjacent seats, allowing separation while still keeping the layout efficient. From the cabin floor to the highest point of the overhead surfaces, the internal height is around 2.6 meters. This was intentionally maintained to reduce the feeling of any claustrophobia and improve comfort on a 21-hour ultra-long-range mission. Moving forward from the main entry area, the walkthrough enters the cockpit section through the forward access passage. The pilot and co-pilot seats, cockpit glazing, control yokes, throttle quadrant, and rudder pedals are represented to give an indicative flight deck layout. Detailed internal instrumentation has not been modelled, as this was considered outside the scope of the current CAD portfolio. From the seated pilot position, the VR view allows cockpit visibility to be accessed directly. The wide forward and side glazing provides the intended pilot viewing angles, with the layout developed to give a representative FAR-compliant field of view. Behind the main pilot seats, two additional observer or crew jump seats are included. The view then moves up into the pilot rest area, positioned above the forward cabin and access from the cockpit, providing a dedicated rest space for flight crew. Starting with the aircraft electrical systems, all electrical power sources feed into a central distribution system, shown in dark blue. On the ground, power is supplied via the external ground power unit near the nose landing gear. The APU in the aft fuselage provides onboard power, while in flight, engine-driven generators become the primary source, routing power through the wing route in the main bus. Batteries are located in the forward avionics bay alongside the main bus. This region acts as a central electrical hub, supporting system startup and providing backup power to critical systems. From this hub, power is distributed to flight critical systems, including cockpit avionics, flight control computers, and control surface actuation, ensuring a reliable supply to essential functions. In emergency scenarios, the ram air turbine provides an independent power source, feeding directly into the main bus to maintain operation of essential systems in the event of total power loss. A secondary distribution network, shown in cyan, branches from the main system to supply non-critical systems, maintaining a structured and layered network. Within the cabin, power is distributed to passenger and service systems, including in-flight entertainment, seat power, lighting, galley equipment, lavatories, and crew rest areas. Power is also routed into the wing through the wing route, supplying fuel pumps and leading-edge systems such as anti-ice through a span-wide distribution line. Moving on to the aircraft fuel systems, the red feed line represents the main proportion of fuel path. Fuel is delivered to the engine from the inboard collector region and the wing route, where the control supply is stabilized before being sent onward to the engine. The purple transfer lines show the internal fuel movement across the wing tank system, with fuel from the outer, mid, and inner tanks progressively transferred inboard towards the collector, allowing the tanks to operate as a coordinated network. The orange and white features within the collector region represent the boost and standby pumps. Together with the central boost pump, these define the inboard wing route as the main fuel management and feed zone. The pink trim transfer line connects the main fuel system to the tail-mounted trim tank, allowing fuel to be moved longitudinally for the center of gravity control during long-range operation. The lime green APU feed line shows a dedicated branch supplying the auxiliary power unit, integrating it into the wider fuel system. The yellow cross feed line connects both sides of the aircraft, allowing fuel balancing and redundancy rather than operating as separate systems. The dark green refueling line represents the ground refueling and defueling path, linking the refueling point into the main inboard fuel network. The dark red dump line provides a dedicated path for fuel jettison if the aircraft weight needs to be reduced. Finally, the upper vent and orange surge pathway represents pressure equalization and overflow management, separate from the main fuel flow. For the main landing gear extension, both hatches open first, after which the gear rotates out through approximately 90 degrees before the inboard door then closes, driven by a simplified actuation mechanism. For retraction, the mechanism is the exact same but in reverse. Similarly, the nose landing gear's hatches first open, followed by the main strut extension, following a similar simplified actuation mechanism. The cargo bay doors are modeled with a revolute connection, allowing them to open outward to approximately 100 degrees before retracting closed again. This gives a representative door motion while keeping the rotation within a realistic operating range. The ailerons are modeled to counter-rotate using revolute connections, with deflections limited to approximately plus or minus 25 degrees. Similarly, the elevator and rudder are modeled with revolute connections, with deflections of approximately plus or minus 25 and 35 degrees respectively. The spoilers and flaps are combined into a single low-speed deployment animation, using revolute connections for the spoilers and point-on-line for the flaps, with deflections of approximately 30 degrees for the spoilers and 35 degrees for the flaps. Finally, the slats are modeled using a combination of point-on-line and revolute connections, allowing forward extension with a slight rotational component during deployment. Overall, the model has been developed with a clear handover strategy in mind. The use of a top-down, parameterized approach means that key design changes can be made at the skeleton level and propagated throughout the assembly without requiring major rework. In addition, a full revision history has been maintained throughout the collaborative lifecycle platform and saved into the Group DHF, capturing design changes and iterations throughout development. This provides traceability and allows future teams to understand how and why the model has evolved. Thank you for watching.